Hey guys. Can you hear me?
Hello.
Hello, everyone.
Hey,
Hey.
can you hear me, guys?
Yes.
Loud and clear.
I can see myself there.
Okay, let me ask you, can you see my screen? There's a blue and a green.
Yes.
Yes.
Can you read the blue text?
Yes.
Yes.
The green text you don't need to read. That's for me. The blue text is going to be, I can make it bigger if you need me to.
No, it looks fine.
It's fine.
Okay. Okay, so what I want to talk to you a little bit about today is just to kind of orient you on DevOps and SREs and what we do, and to try to get you on the process of thinking about things from an operations standpoint, if only just to empathize with what operations people are supposed to be doing, and to try to get us on the same page so we're all working together to solve the same problem. That's really what DevOps is about. It's about bringing developers and system administrators all under one roof and to try to work together instead of working against each other. Because what an operations guy wants is stability and reliability, and he doesn't want to be dealing with alerts and firefighting. And what a developer wants is to be able to turn things over fast and make customers happy and ship cool products and things like that. And for a long time, historically, they were working against each other. And then the DevOps movement started to try to join them into the same framework. So that's basically what it's about. DevOps is an idea, it's a movement, it's not a job. Nobody is a DevOps engineer. An SRE is a job. A production engineer.
Joe, I'm sorry to interrupt.
Developer is a job.
Sorry to interrupt. Some of the guys are fighting a fire right now. I don't know if you know, Andy, William, Tom, they're not here. I don't know if you want to go on or reschedule, or then, you know, talk to us and then talk to them again. So
He's recording the video.
Oh, okay.
Yeah, I'm recording this, so it's okay if they miss parts of it.
All right, go ahead.
So for my money, what a DevOps team looks like is what they do at Facebook and what they do at Google. What they do is they have teams of about 8 to 12 engineers. Most of them are developers, and some of them play some sort of operations role support for the developers. Now, what that means is that they all sort of share responsibility and share control of everything. So the developers will do some on-call duty, they will firefight, they will do different things that operations people are typically tasked with, and the operations people will participate in development. So it's kind of a blend, but you have specialties. I mean, I'm not a developer, I'm an operations guy, but I can do development a little bit. And that's kind of the tack I want to take with you is I'm not training you to do operations, I'm training you to be able to participate in the DevOps environment constructively as a team player. And that means going from a full stack developer role to kind of a systems engineer role, where you're looking holistically at the whole platform and you're trying to drill down to solve problems that have to do with things you care about and things you're interested in. And that's performance, reliability, and operation of the services. But it's not your job to automate everything. Your job as an automation guy is to automate your tests. That's what you want to automate, because that's what's going to add value to you and your development work is automating your tests. So you don't have to repeat all this dumb testing that you've done in the past by hand. Sorry, my daughter's here. So what I do as an operations guy is try to solve your headaches in terms of managing the infrastructure and access to the infrastructure and controlling your access to the infrastructure and making sure you have the ability to help with the firefighting. Because right now, the company's faced with a problem that lasts for about 5 minutes, which means the clock is ticking from the time we notice the servers start to clog up and fail to the time the event is resolved, and then we have no data to collect. So we want to get you onto these machines and help us triage it and try to collect data as meaningfully and as quickly as we can so we can diagnose the problem and fix it, not so we can keep going back and forth arguing about what we think it is. We want to be able to say definitively what's going on. And what I'm going to show you with htop today is how to do that process with the bugs that we've got right now. And that's really the takeaway for you for this talk, is not so much all my high level jibber jabber, but just mastering htop's interfaces to try to answer questions you have. I'm not going to solve all the problems that I ask you about today. I'm going to try to pique your interest in going about using tooling to solve these problems yourself and ask the right questions. It's not getting to the answers right now, it's getting to the good questions and having a good perspective. My door is always open. Don't be afraid to ask me anything, especially if it's about something you read online related to DevOps or SRE work, because a lot of it is terrible because it's been taken over by marketing. What was a good idea from a technical standpoint, it's just been ruined by product managers and people trying to create roles that don't make any sense, that don't add value to the company if the company's really trying to succeed. And what an SRE is a serious role to try to help you succeed as a DevOps oriented team. So that's part of my role here, so is to evangelize a little bit. And that's what I'm going to do for the first 10 minutes of this talk. Then I'm going to show you how this stuff works. And then I'm going to go back over the stuff I showed you. Okay, it's going to be very fast at first. And then I'm going to make time for questions towards the end as we go over it again. Okay?
Sounds
On the
good.
same page?
Yeah.
Sounds good. I don't have the camera on because I'm eating.
What you eating?
Just frozen food.
Okay.
Here's the talk. Here's the talk. This is about HonorLock's DevOps experimentation and moving forward with what we want to do as a DevOps team. And what I'll tell you again is you should look at the teams that Google created and the teams that Facebook created around doing server engineering work and knocking up services and taking ownership of something with a very small team and just doing amazing things with it. You don't need a lot of talent, you don't need a lot of personnel, but you need to be able to automate things effectively and do your role well. And you can do amazing stuff if you have the right background and perspective on it. So that's where we'll start. And here's what I'm going to try to go about presenting to you is that all these problems that we're solving are just new context for old problems. The problems that were solved by Unix engineers when they created Unix in a multi-user environment and a kernel and a user land and all this stuff, it's about taking a common thing like a binary executable on your file system and running it in different contexts, and those contexts being context sensitive results. So when one user runs something, something happens, a different user could run the exact same program and get a different result. And you could do that, you could shape that in many million different ways on Unix, and that's all we're doing in modern times, is just running the same applications in virtualized environments, Docker containers, on Macintoshes, on Solaris machines, on the cloud. It's just changing the framework, but the applications aren't changing. You're just running them in different ways. What you want to do as an engineer is try to make your engineering products compatible with that, which means when you're developing software, you don't like global variables. You try to use variables that are scoped exactly to where you need the variable and nothing else, and then it goes away. You don't have a big dependency chain, and the less things you depend on, the more context you can run it in. So that's a lot of what we're doing nowadays. It's just reinventing Unix and putting it in a high availability, multi-user, multi-tenancy, multi-cloud environment. So Unix systems were built in the 70s. This is not a historically accurate assessment by any means. I'm just talking off the top of my head about the things I want to focus on for this talk. The thing is, Unix is implemented in C. C was designed to make a Unix system. It's not a Lisp engine. Lisp is very mathematically beautiful to people who like theory and want to reason about programming languages and structures, but it has no syntax. It's ugly as hell. It just looks like function calls with weird parentheses everywhere. And that's all it is. It's just math. It's just functions inside of functions inside of functions. Well, what C is a lightweight language. Nobody wants to write assembler. It's a compiled language, and it's got a very easy to understand, very readable and flexible syntax. It's not a lot. It's not hard to parse. It's very easy to work with, but it's nothing like Lisp. It's actually very easy to read. So the thing about Unix is that it presents a memory model that's linear, and it's sequential, and it's virtual. And I'm going to get back to that later when I show you some things on my machine. So you have addresses and memory addresses, and those addresses don't always map to physical objects. It's what virtualization is about, and how swap works. So it's just a bunch of numbers that it keeps a little bit of indirection between what it shows you as a programmer and what it's actually doing with the hardware. And everything that's not in RAM is a file. That's sort of the Unix mantra. It's if you're not dealing with strings and data structures and memory, you're interacting with a file somehow. It's a file descriptor in some way. If it's a socket, device, these things all sort of have a file system basis somewhere, even in the proc file system. Again, it's just giving a file system interface to things doing with processes. Everything is about this common, very simple interface. There's not a lot of complexity in it, and that's what makes it powerful, because you can plug anything into a file. You can plug any file descriptor, can be treated arbitrarily. And that's what makes it very powerful. You can run things that are designed to process files and have them handle sockets. It's multi-user, it's multi-process. These are different contexts that you can run the same program in. It's open and shared and for collaboration. When they design Unix systems, they designed it for people to do things together. It's not a single user system. It's designed for many users. It's got a very basic permissions model on the file system, and that was it. Everything else that's been added to this, just more context. So the context-sensitive interfaces that are relevant for operations are consoles and terminals. Those are the very early ways of interacting with any kind of Unix system. A console and a terminal, a console is just a type of terminal. A terminal is a more general term for something that's got like a modem interface. It's got a baud rate. It's got a buffering interface. It buffers things, line buffers, character buffer. You can control that, how it buffers things and how it presents it to it, but it's mainly for things to be seen or things to be printed out and read. So that's your user interface, and it's still survived after all these years. I'm still doing interesting things with terminals because it's ubiquitous. The thing is, when you're doing DevOps work, all you have is a terminal on the server. So if your whole workflow is oriented around terminal interfaces, you're going to be right at home. And that's the way I work. All of my tools are based on terminal interfaces. And if I need to look at something really pretty, I put it on my laptop. And don't use X. X is terrible. I use a nice Windows machine or a nice Macintosh. Those are great. Well worth the money. Shells and processes. What a shell does is gives you a way of managing and launching new processes and interacting with things in a scripted way. So C is kind of cumbersome for an administrator to work with because it requires a little planning, forethought, compiling, dealing with this, and an administrator just wants to get the job done. And a lot of times the things that are really compiled and ready just need to be assembled and organized in a batch way, and that's what shell processing do. Shells let you do things with compiled objects, and if you use it smart, and you pipeline to compile things together, it can get real good performance out of it. But you have to be smart. And that's what an operations guy brings to the table, is how to hook all these things together in ways that make sense. It's not a lot of hard work. So one of the things that it does is fork. You have a way of taking a process and creating a new one that's just like the one you've got. Exec is a way of changing the process that you're running into something that's completely different by rewriting it exactly at where it stands. Pipelining is where you take two processes and chain the output of one to the input of the other. You can do that arbitrarily, but the real bang for the buck is co-processing, where you take some process and you run it in a different context, where you have the input of one process hook the output of the other, and vice versa. So they're like binary stars. They're just sort of dancing around each other, and you can cause all kinds of funny problems with buffering and staleness. You want to think of that as a driving. You have one process that's driving something else, and that's what a lot of what system administrators used to do with terminals and modems, is we would have something called an expect script, which was a way of driving a terminal process. It's written in the tool command language, TCL, and it's a very ubiquitous tool for system administrators who have to deal with prompts and things that are happening on the terminal, because the terminal is a little bit more sophisticated and also slower than standard IO, than the things that are happening on standard in, standard air, and standard out. When you hook those things directly to each other, you get a lot of speed. The speed is basically as fast as your operating system will run. But if you insert a terminal anywhere in the middle of all that, and some of the stuff I'm going to show you does this, you got some performance problems, and you're gonna cause some issues, and we'll see that. So IPC and Berkeley sockets, again, everything's a file. When you're doing a process control, when you're doing process interfaces, you've got some shared memory segments you can deal with. That's kind of not a file and not a piece of memory, but it's a little bit different. And Berkeley sockets, which are the beautiful way of doing server client programming. And they're ubiquitous. So I'm just going to hit that. Users, groups, and roles, just going back to the same things. It's just running things in different contexts.
I don't think we see that, Joe. You're running something in your other screen, because I don't see it.
I'm not doing it. I'm not running anything right now. I'm just giving you a preamble.
Okay, I thought that you were running some testing and showing us.
Yeah, I'm going to show you. I'm going to show you all these things. Right now, I'm telling you what I'm going to show you. Users, groups, and roles is just different contexts and different security apparatuses for running the same job. Context switching. This is really what I want to talk to you about because it relates to htop and strace. What a context switch is in a kernel environment is where you have a program that's running. You launch a program. I don't know what it is. It could be a PHP backend process, and it's processing the PHP parts. The parts that are native to PHP that aren't interfacing with anything else. It's just PHP operations. That stuff runs in the user space as the user you launched it as, and it goes nonstop. There's nothing that's going to hold it up other than the kernel descheduling it because it's got something more important to do. It's going to put it on the CPU and it's going to run it as fast as the CPU will let it. And the only time that gets screwed up is when you need to do something with the system. And that means you're interfacing with libc. Libc is the only interface a process has with the kernel to get the kernel to do something on its behalf. And what happens with a context switch is you call out to something in libc. That's the basic Unix interface to the kernel. And libc, what libc does is it puts a special process instruction on the CPU that says to the CPU, hey, I'm done. Set aside what I'm doing right now and go make this system call and tell the kernel do this for me. And what the kernel is going to do with that instruction from the CPU is say, hey, do I have the right permissions to execute this command? So it's going to interrogate the context of the system call, look at the process, look at the process's metadata and the permissions related to it and the user and all the other stuff and say, yes or no, I'm either going to do this or I'm going to just reject it. Most of the time it's going to do it. And then what happens is the kernel is running this thing without any restrictions. It's running it as a root user. It's interfacing with devices. It's doing whatever the kernel does to try to do things that you have no business doing yourself, because that's the security model. The security model is all handled by the Unix kernel. The user land is just stuff that you'd like to do that's safe to do. Event handling is another part of how context switching happens. Well, there's something, the timer could come in and deschedule your job. But for the most part, what I want you to focus on is the system calls, because that's what we're going to look at today, system calls. The system calls where your program needs to tell the kernel to go do something for it. And it does this by calling into libc. Your program is linked to libc dynamically somehow, and you make a call to that program, and that program has that special instruction for the CPU to signal it to say, hey, you know, I need you to do something for me. Signals are also part of that. A kernel is responsible for signal delivery and signal processing and signal handling, but you register that through libc. You register a callback. You can set a signal, and the kernel has to figure out what to do to interrupt that. And sometimes when you're in the middle of a system call, when you deliver a signal, a lot of mess happens, especially if you go back into the system calls. That's generally a no-no, but there's been a lot of engineering work over the past 30 years to let you mostly do what you want to do in a signal handler. POSIX threads. This is also a nice new, relatively 20 years ago technology to allow you to do something outside of a process context. It's a little more efficient. It's just an optimization. It just lets you, instead of doing a copy on write of a process when you fork it, it's just going to leave the memory intact and let you run it in a different execution context as if it were its own process. And that's basically what that's about. So what I want to talk to you about is what I'm going to show you today. And most of what I'm going to show you today is not my infrastructure, but I'm going to tell you about my infrastructure because I'm going to repeat this several times as we go over different aspects of what operations work could be. These are just to tickle your fancy, to show you what's possible. These aren't suggestions for how Unix should operate. They're just sort of pie in the sky. Here's what can be done without a lot of work. What I use is Solaris. The nice thing about Solaris is that it has things that Linux wishes it has and still trying to get. One is ZFS. If you ever work with ZFS, a real file system like this, you don't want to part with it. It's very difficult for any kind of administrator to look at a Linux file system and compare it to ZFS and say, hey, I want to do that. It's not. They're not the same. They're not in the same ballpark. And even the open source efforts to try to port ZFS to Linux, they're just not there. So I'm holding out on switching to Linux when the ZFS finally becomes prime time. Zones. Zones are actually kind of an old school thing that's been similar with FreeBSD jails. I don't know if you've done any virtualization work, but you probably have experience with VMware. what VMware does is kind of give you a fully isolated environment to run whatever operating system you want. What a zone is just a kind of localization of the existing operating system to a different context, to its own operating system. It's got its own init, it's got its own startup, it does all of that stuff, just like it was its own operating system. It's got its own IP space, everything. But it doesn't have its own resources. They're shared. They're shared with the parent, but it's just isolated for security reasons. And that's kind of has advantages and disadvantages because you're not tied to the hardware when you try to spin up more virtualization. With VMware, you're kind of stuck with the number of CPUs you have to allocate and dedicate, and the memory. You're blocking out chunks of memory. It's not shared. So the modern virtualization techniques and Docker is just like this. It's shared. You can spin up 1 million Docker containers as long as you have CPU resources to process all the active jobs, you're in good shape. DTrace, this is really a valuable thing with this kind of pie in the sky for Linux right now. It's trying to get a dynamic kernel tracer. What a system trace call will do is let you look at all the times libc has to make that special system call into the kernel, and it has to do a context switch. It's gonna show you all of the times that happens in your program. That's all a system tracer does. What a dynamic tracer does, so a system trace is kind of limited to one thread. It's going to trace whatever that thread of execution is doing. A dynamic tracer like DTrace is kind of giving you the kernel global view. So you can look at things on the perspective that the kernel takes on everything. So you can look at what the kernel is actually doing with those system calls. And you can instrument the kernel, but you can also instrument the user space and look at what everything is doing across the board, not just one processor or one thread. So that's what's really valuable about this. And when you get it into your dynamic programming languages like PHP, you can do a lot of very interesting profiling and kind of look around at what's happening on a live system without actually screwing up the system. It's meant to be kind of transparent. It's meant to be fast. It's not supposed to interfere with what's going on in production. These are things you're supposed to be able to use at some scale with some intelligence on a production machine to kind of ask questions that you're currently not understanding about your infrastructure. And that's what htop is telling you, things about that you don't know. Htop is sort of like a firefighting tool and also preventative tool. It lets you know what's happening over time. If you gradually pay a few minutes every day to looking at htop on these systems, you'll get your own sense of what's going on well before the metrics will pick up when you do monitoring.
Hey, Joe.
Yeah.
Does DTrace run ring 0? Or are there any calls that it doesn't see?
It runs basically DTrace is kind of, it's instrumented in the kernel. So what people do is they have to write their own hooks. They write DTrace specific hooks in the kernel. And what you do is run a little awk-like programming language to kind of hook into those hooks and run and probe those hooks and count how many times those hooks are entered and exited.
Okay.
It kind of runs as kind of a design by contract system. It's like, for the most part, at least when you do DTrace in the user space, you're looking at entry and exit of a function. You can look at the arguments and you can look at the return values.
Right.
It's kind of hooks right before and right after you do the program. So you can actually run profiling on a function call and see. And you can do that at the dynamic level too with the right tooling. But Linux has got a long way to go to catch up to that. DTrace is 10 years ahead, and bpftrace has only been good for about a year. And it has it's really solved the problem at the C level. It's great. It's great. With a 5.3 kernel, bpftrace is beautiful. But getting all these other programming languages like Python and Perl and PHP to put all the probes into their ops trees and things like that, so you can actually do things at that level, that's a long way off. That just requires a lot of effort. It can be done. It's just whether or not people will invest the time. So I'm going to tell you about that. So those are the three things I really value about Solaris. Otherwise, it's just another Unix system. And nice thing about Macs is they have DTrace. I'll give you the thing that doesn't work with htop on a Mac is that the system trace, it doesn't work. The S button doesn't work, the S key. But I have a very simple fix for that. It's just a script. It's just a DTrace script. And it just works right out of the box beautifully, but you have to do some things at the kernel level to enable DTrace. You have to boot into rescue mode and deal with the role situation en route. It's all documented online. It's not hard. I'll explain how to do that to you, how you can do that sometime. Time strikes. So the other thing about my infrastructure that's sort of unique is it's a hub and spoke model. So I have a Zeus, which is my sort of thing I do everything on. I do nothing locally, and I do all my development, I do all my prototyping, all that stuff on Zeus. And Zeus is actually part of a production infrastructure as well. But the only things about the production infrastructure that are relevant to Zeus get shipped all over the planet. I ship it to Frankfurt, Germany. I ship it to Brazil. I ship it to the West Coast. I ship it to Washington. I ship it to Australia. And that just makes my system that much faster because all of the interesting dynamic interactions the user has are with those endpoints, not with my Subversion server. All this stuff is just delivered in Subversion checkouts. So it's kind of the opposite of what you would do or what you would do with an RDBMS, but it's just heavily cached. Everything is sort of regionally cached. So there's some chance to get stale hits, but you can also refresh and get it live. It's VPN based. It's a VPN based network, and it's got a zero trust architecture. I don't have time to cover zero trust architecture, but I will when we do security. Okay, there's my Windows laptop, and then we get to start talking about, show you some of the stuff. What's nice about Windows is compared to the Mac, I use both. My Mac is my home go-to machine, but it's very old. I had the company buy me a Windows 10 because this is just a beautiful way of doing DevOps work with Docker, because you don't have Docker on a Mac, and I have a very fully functional Linux environment on here and called WSL. It runs Ubuntu 20, and all of my Unix tools work natively in Unix. I don't have to. I have an Emacs server that I run in Windows as a Windows binary, but that's just for looks. I can run the same thing on the terminal on Emacs. So here's my Unix tool chain: Git, ZSH, Emacs screen, PIDs, SSH, Orthros, and htop. PIDI is a terminal driver that does co-processing. I have a driver script. What PIDI does for me is it processes passwords. So I only have to type my password in once for as long as the Unix server is alive, and it will cache it no matter where the password needs to be delivered through the terminal. And the terminal can be connected to an SSH machine anywhere in the country. I'm going to deliver my cached password to it. What Orthros does is allow me to use one-time processing as a challenge, OTP, one-time passwords as a way of federating all of my logins. So I have one password and one master password for all of my one-time password logins, but because of the challenges and the way this thing is distributed and set up, nobody has the same version of my password, has it raw. Okay, htop on WSL, terminal UI, top matter, CPUs, hyperthreading. Okay, let's just, I'm just gonna go, this is the screen you should refer back to as I'm going through htop, but this is the only meat for you as far as this talk goes. System trace is just what I said. It's about finding that boundary between what your program wants to do and what it needs the kernel to do on its behalf. And it's going to do a context switch each time, and we're going to monitor every time it does that. strace is instrumentation on the libc side. This is just the binary executable that monitors system calls. You can run strace as a wrapper. You can run strace and then call a command, and it will put strace probes into that call, and she'll put a right to standard out every time it makes a system call. Or you can hook into a process like it's a debugger, a live debugger on something that's running live. And that's what we're going to do with htop. It does bare bones real-time process thread system calls to standard error. And what I've got, the difference between I have a stock Ubuntu htop. My Solaris htop is mine. I had to build this myself. I ported it to 11.4 because nobody bothered to. And I added the S and L features and the E features to it. There's some problems with that activity that you can't avoid. The differences in the way the Linux threading model is managed compared to Solaris. With Linux, a thread is basically identical to a process. It gets its own PID. It just doesn't copy. It doesn't do the copy on write aspect that a thread would do. So it's a lot of the tooling that's built around processes works identically for threads. It's just, you just feed it a PID, process ID. Solaris is different. There's two layers to the onion. There's a process ID and a lightweight process ID. And that difference has to be represented in the htop deltas, and you'll see that. Solaris, like FreeBSD and like Macintosh, the tracing binary is called truss, and Linux is called strace. They're not the same name, and the way htop works, it just calls out by name strace with certain arguments. So that's just not going to work anywhere else. The L key on Linux is based on LSOF, lists of open files. It's a very flexible tool. It predates the proc file system and has no chance of ever working on Solaris. It works on FreeBSD. I think it works on Mac. So the L key will work for you no matter where you are. But on Solaris, I had to do some work. Htop on Zeus is the Solaris version I'm going to show you. Htop on a regional OCI zone is I'm going to show you how do I connect to a virtualized environment and how htop looks in that virtualized environment and what are the salient differences. Again, it's just running the exact same things in a different context. There's no difference between an Apache web server on a bare metal or in a virtualized environment. It's just the context that changed. And you can do different things in different security ways by thinking about that. This is the last slide. DTrace. I talked a lot about this, so I'm not going to cover it. bpftrace is kind of the promise of bringing DTrace technology to Linux. This kind of stuff is really bread and butter for systems engineering work, because it tells you everything you need to know, and it gives you tools to ask questions that nothing else can answer. Okay, that's the whole sales pitch. Now we go to the demo. So here's my Windows PowerShell. I got on the right screen, I've got an Emacs that runs as an Emacs buffer that runs as a Windows binary. And I've got this PowerShell that's a Windows binary. What I can do is now I can get into the WSL interface, which is going to launch Ubuntu 20.04 and drop me in as a user. I'm going to show you the back door. You can run this as root, and it will drop you in as root. So if you ever screw up your login credentials on the Ubuntu that's underlying all this, this is your vehicle in. This is your back door. So I'm in there as root. You can see the path is I'm still in my Windows file system, so it understands my Windows file system. That's not hard for Linux to do. The hard part was getting Windows to understand the X4 file system, which they did. You can see it down here. I have a Linux. My File Explorer on Macintosh has all of the stuff. It's all of my Unix file system is available to the Windows applications because they now speak the same language. So that's nice. That's a really nice part about this is there's so much integration. And the thing is, I can call Windows executables from Linux. I can't do the other way, but I can call because of the context, right? I mean, the parent server is Windows, and Linux is running in a virtualized environment. So what the Linux kernel will do with an executable it doesn't understand, it will just farm it out to Windows, and Windows will run it. So that's kind of, it's a very beautiful interoperation here, and I have a fully functional Unix environment right on the system. And it takes nothing to get this set up. Everything is just very easy from the command line. So what I'm going to do is I'm going to show you a tool. I'm going to open this up all the way called vmstat. I'm going to show vmstat. Okay, what vmstat is telling me about is giving me kind of a dashboard systems engineer type look at what the system is doing. So there's nothing in swap. There's a substantial amount of free memory. There's some of the memory is buffered. I don't remember what RMB stand for. It's not relevant. I'm just going to talk about the things I see. The cache, there's a little bit of memory that's cached. There's no swap in, no swap out. There's no swap activity going on. The IO is the bytes in, BI, BO, bytes out. I'm here now. And you can see that the columns are a little bit off. They're shifted to the right a little bit. System calls, I don't remember what IN is, but the one I want you to focus on is CS. That's the context switches. So you can see that there are some context. This is vmstat 10 runs every vmstat every 10 seconds and probes it. It's got about 60 system calls every 10 seconds going on. And those system calls are basically this damn process reading input and output from the terminal. So those are the calls. Those are, every time it's hitting a libc job that it needs the kernel to do, it's making one of these calls and this counts it. So there's a user, system, idle, and wait. System, this is the CPU amount of time. Idle, it's all totally idle. There's nothing going on. Wait states are just whether or not the CPU is stalled, and the status. Okay. So that's what vmstat tells. The point is the context switches. So now I want to look at, I'm going to do a couple of things here I need. They're just chores. I haven't figured out how to automate yet. This is something I'm going to show you a screen that does this. Yeah, it needs it. It's something that depends on. I don't know how to get to it anyway. Let's run htop. So here htop is showing me something that looks like it has 12 processes. There's 12 CPUs. There's actually 6 cores. There's 6 cores and 12 logical processes. That's what hyperthreading does. Hyperthreading presents as two independent CPUs per CPU. So you get double. Linux way, that's the Linux way of dealing with hyperthreading. Everybody does that. And so does Windows. Everybody does that. I'm going to go through these things. Memory is just telling you it's got 15 gig allocated to it. But again, that's virtual memory. The Windows machine only thinks it has 32 free. It has 20 free, and there's 16 of them for Windows for Linux. So there's a discrepancy there that you need to think about in terms of how virtual memory works. Ethernet. That's just the internal LAN that the Ubuntu system is on. The Windows machine is the host, the router, and the Ubuntu machine is somewhere else. It's on the same network. What I'm going to show you, there's a couple of things here. Tasks, threads. There's 2 threads. The threads are colored green. Those aren't processes, but they have their own process ID. And only one thing is running at a time. There's nothing going on. There's no load. There's 4 gig of swap that's managed by Windows. There's no swap disk. There's nothing like that. It's been up for 6 minutes. I'm going to look at the tree view, show you exactly how the processes are laid out. This is just pressing the T key on htop. So there's an init. This is not a system D interface. When Windows ported the kernel, they got rid of all the system D calls, just like Docker did. There's no system D. There's its own init. It does almost nothing. It doesn't launch any processes. This is the whole process table for the running kernel. It's just some init stuff. It's just forking init a couple of times and it launches bash. And then my bash root shell launches htop because I typed that into the command line. These are two jobs. I'm going to look at the environment. That's the environment that the kernel passes to init. I just press the E key. I'm going to go back with the Q and look at the open files. This is the L key. This is very important to use all 3 keys, L, E, and S. The L key will tell you which on these file descriptors, what the file descriptor actually represents. So it's got some dev null file descriptors. That's standard in, standard out, standard error. They're all dev null. So this is a daemon. It has no way of there's no way to interact with it other than through memory. And it's got some other things going on. It's got some socket here. Get out of that, and I'm going to do an strace, but I'm going to do 5 first. I'm going to press the S key, and that one blew it up. So you can tell there's some work to do here for the Windows developers because this thing is just launching seg faults in a succession. It's going to break everything. So these are signal calls. And now my kernel, I've lost my shell because this thing's so screwed up. That's why it's not prime time yet. There's things that don't work quite right. So I'm just going to go back in as me. Let me just clear all this out. This is logging in the normal way. This is as me, not as a root user. And I have my own environment. And let's look at htop. I have this alias, so I have some passwords to type in. So here's what it looks like for me. There's those 2 threads. One of these threads, I guess it was 5 and 6. One of these threads is just going crazy. There's the thread that's not going crazy. It's sitting there in an accept, which means it's waiting for it's a BSD socket. It looks like the number is 9. So let's look at what 9 is. Let's press L. 9 is this Unix socket. So it's sitting there in an accept on this Unix socket that's with this basic underlying file descriptor. This is the kind of Q&A you need to be able to do when the system is down installed in production. You need to be using S and L. Here's here's my sudo command. That's it. I have a Z shell. I'm going to show you the environment for that. That's just the E key. It's very simple. This is what the WSL is providing. And here's some more inits. Here's htop. This is the actual command that I'm running. Let me put it in a tree view so you can see it more structurally. Here's these 2 init threads. One of them is sitting there idle. One of them is, I don't know, seg faulting like crazy. And let's see, what are the other things I can show you about this? I think that's basically what I want to cover. Here's some of the other details that I've added. I have an ability to look at kernel threads. There's no kernel threads running because the system's not doing anything. This is just my Ubuntu one here. And it's pretty much the same information I tried to tell you before. Let's see. Let's go to this. I'm going to run this command. I'm going to run pity screen. Now what pity is doing is this is that pseudo terminal driver I told you about. It's going to launch SSH agent, which is then going to launch screen itself. There's a lot of wrappers here. SSH agent just sets up a way of providing a cache for your SSH password credentials for your keys. And it runs the command within that environment. Now, Pity's kind of doing the same thing, but it's putting a terminal driver and it's putting a terminal in between co-process between the Pity driver thingy and the screen process that SSH is running. So these are working together, and it's going to drive my terminal, watch my terminal for prompts and fill them in, or prompt me for things it doesn't know how to fill in. So I'm going to show you how that works. I got blown away. That seg fault really did a number on it. Okay, so what screen is a multiplexing way of dealing with terminals. So at the bottom is my ZSH mode line. It's telling me that I'm running ZSH in Windows 0. And that's what I got there. And up at the top, it tells me which host I'm on. And let's see if I can scroll down a little bit. I'm going to change to my Unix user. On the right is a Git branch that I'm in. I keep my home directory on GitHub. And it's got a lot of tools in it I'm going to show you over the course of time. Let's see what else. Let's run htop again. So it doesn't know my password. The system password Pity driver thing is what this Pity driver process is doing for me. It sees the prompt and it's going to ask me interactively, give me the prompt, and I'll feed it back to you and keep a copy of it. So I'm going to do that. And it's done. So here's my Pity, here's my htop process. And here's the tree view of all that stuff it launched. I'm going to scroll over a little bit so you can see it. So Pity is driving my terminal, and it forked a process to drive the I/O, the standard I/O and standard I/O, as the input and outputs for one of it. Then it launches a Perl command, which is the driver, and it hooks the driver up to the terminal on both ends. And the terminal on both ends is hooked up in the reverse order to my screen. And whatever I can see on the screen, this driver can see, and it'll just transparently show me what's on the screen, but it'll also look for password prompts and fill them in. So that's what all that stuff is doing. Let's do something interesting. I'm going to log into Zeus. So I logged into Zeus, which is my infrastructure, my hub server, and I'm going to run htop here and show you a little bit about the differences. The first two columns are different, right? There's a PID and an LW PID. And there's also some interesting memory information here about the ZFS memory management. That's all just Solaris specific. But everything basic other than the zone ID just tells you which zone this process is running in. The global zone can see all processes, but if I do this from within a zone, I will only see that process. So let's look at this daemon. This is a security daemon that handles IKE traffic. This is part of the VPN. I'm going to trace it and see what it's doing. This is just pressing the S key on here. It's just running a trace. It looks like it's not doing anything. It's just sleeping. And that's what a process will look like. If it's actually running and not hung, it will, eventually just make more calls. When it's hung, it'll just be stuck there and nothing else. You'll see no more system calls. It'll just be stuck waiting for a system call to complete. And that's what you're going to see on production with this stalled process. Let's look at this HTTPD process. Let's look at this process. This process is running in a jail, it's in a zone. This is running in the systat, running in a zone. It's just some kernel process just trying to keep track of things. This is a lot of what you should be doing with htop as you look through these machines. Is just poking around because you're not going to hurt anything unless you kill a process. And that's K. Just stay away from K or don't run this as root. Let's see. So questions. I'm going to show you what this looks like. I'm going to log into a zone in Frankfurt. Into the www zone. I'm going to show you. Whoops. I know. Do that. So I'm connected to a zone. Now the locking failed because this zone has most file systems mounted read-only. Again, that's sort of running things in a different context. The way to secure a zone for a large part is to remount basic file systems on your global zone on your global system into the zone is read-only, so nothing can change them, and that's a good way to secure things. So my home directory is one of those. There's a lot of other things that are mounted that way in here. I'm going to run htop and show you what it looks like from inside of a zone. The zone IDs, this is just garbage, 666, I don't know what that is. It's probably the zone ID for this zone. Maybe on the global zone, but that's the only zone it can see. There's the lightweight PIDs and PIDs. This is just running stuff inside of, let me look for an HTTPD. There's an HTTPD process running as the HTTPD user, so it's a kid. It might be a mod Perl process. It probably is just a regular Apache server. Let's just look at it with S. So it's sleeping because it's blocking. It's sleeping. It's on read 5, so it's waiting for something to happen on the file descriptor 5. So let's look with L, what file descriptor 5 is. Can't get it. This is part of my bugs. Sometimes it doesn't finish in time. There we go. Let's retry it. So there's the process I'm tracing. Let's see if we can find number 5. And it doesn't tell us very much about what is on PID 5. Looks like it should be 80. Looks like this is probably 3. Let me do. I don't know if I'm tracing the same file or not. Let me try S here. This is in This is just sleeping. It's just not doing anything. That's kind of where most things will be. They'll be idle. But when things are stuck, you want to look at the things that are stuck. So let's press F6 to sort by, or F5. I don't know. I'm just kind of not sure what to show you at this point. So maybe I'll take some questions. Do you get what's kind of happening with the S key and the L key and the E key, looking at a process and trying to figure out what it's connected to and what it's trying to do with the system calls? Yes, no, maybe, hello?
Yeah. Trying to follow. It's a very intense stuff, but yeah, we're following.
Yeah, just let me go back to the slide presentation and try to walk you through the whole thing just very fast again and take questions about anything you have.
I mean, I can.
Okay, so
safely
here's
say I'm lost.
what I wanted to show you. We talked a little bit about the different aspects of Unix and just trying to do things in different contexts. And that's a lot of what modernization is about. It's just taking the problems that other people solved a long time ago and finding new ways to do interesting things with them. And that's a lot of what I do, is find new interesting ways to do things.
I mean, you can follow how you're tracing the processes and things like that. It's a lot of it is.
I'm pressing the S key.
Yeah. A lot of it is, this stuff is a little bit over my head, but I think we get the idea of how you processing tracing.
What I'm trying to encourage is experimentation with htop. Run it as root, do it on the staging cluster if you want to get comfortable with it, and just trying to figure out how to answer questions using the S key, the E key, and the L key about what a process is doing in terms of its system activity, whether or not the process is dead, whether or not the process is waiting for something, what it's waiting for, and for how long. I mean, these are rudimentary questions on a kind of operational level. What's the process actually doing with the kernel? What does it need the kernel to do for it? It's not telling you anything about the code. That's a different level of investigation. This is sort of the system aspect of, well, when you don't understand why something's not working or why things are stopped, and it's stopped because some resource is being either overconsumed or out of available resources or something like that, which is what I suspect your problem is with this blocking thing. Something is hitting a resource limit, and that resource is on a global scale outside of any one operating system. So it's going to be a networked situation where some program is just stuck because it can't get the system to respond to a request because it's out. It's all out of resources. And then what happens is that the HTTPD process comes along and says, okay, you're out of time, I'm going to kill you. And it kills all those jobs. And then suddenly there's resources again and things start working until you reach that point where it's exhausted. Does that make sense in terms of what the strategy is for trying to resolve this little gremlin we're dealing with?
Yeah, in a big picture way, but yes. I have one question. You mentioned something about Docker on a Mac, that you use Windows because of Docker can be used.
I use Windows because of the Ubuntu interface, because it gives me a runtime, gives me a Linux runtime that's highly integrated with Windows. With a Mac, you don't have Linux. You have to run VMware or something and put Linux in its own sandbox. You can do that. It's just not as elegant. It's not as integrated with the rest of the system. That's the only real difference.
Gotcha.
But the thing is, all your server work in this company is going to be around Linux. It's not going to be around a Mac. Nobody runs Macs and servers. They're just crazy to do that.
Gotcha.
So, I mean, any kind of DevOps work you're doing, and reason why I'm kind of pushing you to do this on your machine, if you get a virtualized environment and we can find some way of miniaturizing our infrastructure by putting it in Docker containers, again, you just run it in a different context. We can set up a Kubernetes on your Ubuntu machine, and you can have the full infrastructure at your leisure, everything but the database. The whole thing is testable and runnable inside of a virtual environment. So you can scale things up and you can scale things down. It's being able to scale things in every possible way that adds value to you. Other questions?
Joe, I have to go. Thank you so much. Sorry, I have to go right now. I have an appointment.
That's fine. I mean, we're done. I'm just winding through the slides. This is my laptop. We just talked about that. Htop. This is the key takeaway. This particular slide. Htop. The process list, threads and processes, and these views. The T, key, the filtering, killing. I didn't go into because I don't really need you to kill anything. Process environment with E, listing the open files with L, and system call tracing with S. Those three things, E, L, and S. I want you to add that to your Htop repertoire. And just play. And you can play around on your Mac. I mean, the only thing you don't have on a Mac is a system trace. But that's really the whole ball of wax for what we're facing right now, is that system trace.
Last time someone told me to go play around, that resulted in me having to reformat the machine.
Well, I mean, we're going to try to find ways to make testing and development work as easy as possible in a server environment. So I want to be able to miniaturize the infrastructures to give you something you can run in a VM or in a Docker container or something that actually you can play with and get your hands dirty and play around with. Because a lot of this is just looking around, seeing what's going on, not being flying blind.
I know I'll have to come back to all this because on the list of things that I'm supposed to look at is trying to create a load testing environment just to see what point we're going to collapse. And then I know that's when I'm going to have to come back to all this more. And then I'll be, once again, totally overwhelmed.
Okay, great. Glad to hear it. So there's strace. We talked about strace, what it does. I mean, you can read the man page for strace if you want to, but you really don't need it. Just use the S key in Htop. I talked about my infrastructure, kernel tracing, bpftrace. bpftrace is not, there's nothing to talk about right now. It's not ready for us, but it'll get there. Okay, guys, I mean, that's all I have to talk about. Anything you want to ask me?
I'll go ahead and chime in, maybe just to give you a little, I guess, quick kind of context on my situation. I know in the introduction, or like in the little description in the Google Calendar item that this was effectively targeted at the full stack developers. So I just started as a manual QA specialist. I mean, first and foremost, thank you for all of this. I was like, my jaw was kind of like open, just kind of like agape, amazed by all these kinds of things that you were talking about. I'll be completely transparent and say a lot of it really did go fly high above my head, but I've learned that there's a process to learning things, and I'm not gonna let that make me feel like I could never understand it. But my question to you is, as someone, a little bit more background, as someone that wants to eventually kind of get into the developer role, full stack development actually specifically, and I'm kind of like not going into the front door, I'm going into the side door because I didn't go to school for computer science or anything like that. I'm all self-taught with obviously HTML, CSS, very basic stuff. JavaScript is my main kind of munch thing on. Andy's actually having me study some PHP to get exposed to it, knowing that I have that goal. My question to you is like, I was going to ask you this in Slack afterwards. I don't know if you want to keep this in the recording or not, but what would you recommend for someone in my position with what I just told you to maybe kind of like be able to provide value to the team and maybe kind of taking it upon myself to learn some specific pieces to what you talked about? Or do you think right now it's a little maybe not in my scope and, you know, wouldn't really be like,
Well, I've been here for a week, so I don't know if I'm the right person to tell you everything that there is to do to be successful in honor law. But I can
Well, for
tell you
sure,
as a
for
50-year-old
sure, yeah.
engineer
Mhm,
that what you want to be is inquisitive.
mhm,
You want to be
mhm,
open-minded, you want to be inquisitive, and you want to follow your heart. You know,
mhm,
do your passion, do what you like to do, and be good at what you do. Whatever you
mhm,
do, if you just try to master it, that will carry you through everything.
mhm,
Just be
mhm.
good at what you do and be open-minded and pay attention to things that people that are in the position you want to be in. Pay attention to what they talk about and
Absolutely.
try to participate. Just be sociable, be open-minded,
Absolutely.
and try to be helpful. And that's really, that'll get you very far in life.
Absolutely. Yeah. No, and that's definitely the approach that I'm taking. So I guess specifically with everything that you talked about, knowing that like I was specifically asking you out of everything that you talked about today, knowing that I'm at that kind of like initial stage, would you recommend, hey, you know what, this was all of these things. How about this little thing? Go ahead and munch on that for a while as someone that's currently working and will be working as a manual QA specialist, that I could learn to like, you know,
I
help
think you should
diagnose
talk more
things.
to Andy about that because that's not the, that's, I don't know enough about how the roles are structured. I've been here, like I said, I've been here a week.
Mhm,
I can't
mhm,
tell you how to succeed in magically, not magically, sorry, that's my old boy, honor lock. How
mhm,
to get
mhm,
to the next level in honor lock is
mhm,
the best thing you could do is talk to the people who are hiring in those jobs.
mhm.
Just see what they want, see what they like about you, and just keep asking and keep talking.
For sure. Yeah.
I mean, I can't, what I'll say to you is probably what Andy would say to you is he's setting up some trainings. What we're going to try to get these teams trained on some of these technologies, you know, either informally with some kind of online pursue at your own pace type learning environment,
Mhm, mhm.
or we'll get you formal training. We'll get you in a classroom environment with a lab, and we'll try to get you the training you need.
For sure. For sure. Yeah. I think I might not be asking it the way I want to. I wasn't specifically asking like how to move up in honor lock. I was more so being like, hey, like generally speaking, the skill set that you've listed here, just generally speaking, like taking kind of honor lock out of the picture just to, you know, learn from someone in my position. What would you say is kind of like, because you mentioned so many things, htop, and I made sure to take notes actually as you were
Okay.
talking. Like where would you recommend, hey, you know, maybe get familiar with Linux or maybe get familiar with that, like taking like, you know, uh, getting promoted in honor lock or any of
There's
that.
a
That's not what I'm
million things I
asking.
could tell you. I mean, the thing is, you have to be patient and be perseverant and persist
Okay.
and try to get your questions answered.
Mhm, mhm,
And mostly try to answer your questions doing your own research because
mhm,
those are
mhm.
the skills that carry you through. Like, I mean, this week I wrote my first line of PHP I ever wrote in my life and it fixed a production bug.
Mhm.
Never touched PHP in my life.
I was
Okay,
there,
so
I
you
think,
could,
when you did that. Yeah, that was you
yeah,
just kind
that
of
I
just
never,
said like,
that's the first
hey.
time I ever did any PHP. But the thing is, when you learn how things work in the technology sector, you know what everybody's doing.
Mhm,
Everybody's just got their own take on the same basic concepts.
mhm, mhm.
So if you learn Python, you learn machine learning, you learn AI, you learn PHP, you're going to learn things differently in every environment. Don't try not to be somebody who wants to pick the best of everything. Try
Right.
not to be somebody who tries to be judge things and say, this is the one way to do things the best way.
Mhm,
Don't read
mhm.
Hacker News. Those guys are bad. Don't be like those guys. Don't make opinions about things you don't have any experience with. Get experience.
Mhm.
That's the best teacher. Your own personal experience is what you should go by. Don't take advice from people unless they tell you just what I told you. Figure it out.
Right. Fair enough. Okay, thank you. Yeah, appreciate
Yeah,
that.
you're welcome.
Mhm.
Okay, guys. I'm gonna drop the call. It was good talking to you. I'm sorry I went over. I had a lot to say.
No worries.
You
I look
did.
forward. I look forward to
But
the
yep.
next one.
You're
We're gonna
passionate
do
about
this every
stuff.
week until the rest of the year ends, and we'll see how it goes.
Sounds good, man.
Okay, bye. Bye, guys.
Later.
Have a good week.